So as part of the introduction to rr480, 580, let me share some thoughts regarding how to develop a good scientific hypothesis and good research questions. So while we cover a variety of statistical methods here that you can apply to do science, it's actually not that easy to come up with really good scientific hypotheses or good research questions. So let me start by making it clear that the term statistical hypothesis is actually a misnomer. You're not actually testing any hypothesis at all. My suspicion is that Ronald Fisher, who is considered by many the father of modern statistics, and who introduced this idea, he just made a shrewd marketing move here. So by calling this hypothesis testing, everybody gets to believe that they are doing science. But contrary to popular belief, statistical hypothesis testing has actually nothing in common with scientific hypothesis testing. And that may come as a surprise because, statistical hypotheses are commonly stated in objective section of scientific papers. So you say, my hypothesis is that treatment A is going to be superior to treatment B. But that is completely wrong. So you shouldn't actually do this. If you look it up in Wikipedia or anywhere else to see what an actual hypothesis is, it says a hypothesis is a proposed explanation for a phenomenon. And if you say in your objective section, my hypothesis is that A is better than B, or X grows faster than Y, or this species relies more on this habitat than this habitat, these are actually not explanations for anything, right? So that is actually not a hypothesis. So if you state a hypothesis in an introduction or in an objective section, it should actually be an explanation for something. And you don't have to state hypothesis. There's lots of meaningful research that asks a question or states an objective, but these are slightly different things. So we'll come to that in a minute. Now, if you do state a research question or a scientific hypothesis, I do have 2 acid tests for you to see whether it's a good one. So acid test number 1 is that deep in your heart, you don't already know the answer to your question, or whether your explanation is true or false. And acid test number 2 is, if you're wrong about your explanation, is it still interesting? And to make this a little bit less abstract, I will give you an example of what I mean by this from a previous course participant who was a master's student at the time in waste management, and he developed a particularly good hypothesis that really impressed me. So he was working on soil contamination and how chemicals and bacteria are migrating through the soil. And he made an interesting link to one of the worst drinking water contamination scandals in Canadian history. So that happened at Walkerton. The drinking water supply got contaminated by Escherichia coli, and a bunch of people went to jail for negligence in water quality monitoring. So one thing that he observed in his own research is that Escherichia coli, they have 2 versions of the bacteria. So one type has smooth cells and the other type has these rough surface proteins that you can see here. And the way the detection mechanism works is that there's a fluorescent marker that binds to those rough surface proteins. So only the rough version can be detected and the smooth version is essentially undetectable. But these 2 always occur in mixture. So that's why the testing procedure generally works. But his idea was that what if these smooth versions can migrate faster through the soil than the rough versions, so they might just physically get slowed down when migrating through the soil. So the idea was maybe it wasn't criminal negligence in the testing procedures, but flaws in the testing method. So as the contamination filters through the soil, the smooth ones come out first, they get into the drinking water supply, people get sick and die, and only with some delay the rough versions follow, but then it's already too late. So that's really his scientific hypothesis. So the phenomenon here is the contamination scandal, but it has alternate explanations. So maybe it wasn't criminal negligence, maybe the testing was flawed. And then from that you can obviously develop an experiment with statistical hypothesis, what's influenced by the lag time, and maybe also different soil types play a role, how deep the soil layer is before this has an effect. Maybe there are some circumstances where this testing method would really fail. Now, does this pass my 2 acid tests for good questions or for good hypotheses? First of all, if you truly look deep in your heart, do you know the answer? Whether it was negligence or the testing method? I don't think so. And if he's wrong about his idea, would it still be interesting? Sure thing, right? So then putting those people in jail for negligence would be vindicated, and I would want to know that. So if you do research like this, if you can develop creative hypotheses like this, you can't go wrong. So whatever your experimental results, it's going to be important and interesting. And in fact, I think he applied for an NSERC scholarship to do this research, and it was granted to him. So people recognize good ideas very quickly. If you can come up with something like this, give it a go. So he at the time was just a master's student, and he's now, I think, a lead scientist for a major environmental risk assessment consultancy. So building true scientific hypotheses, this is really the ticket to contributions that people value. Now, to make this point even clearer, let me also give you a counterexample of a really weak hypothesis. So this was from a student who actually did quite an elaborate study on a land reclamation project. So that was a collaboration with a mining company, and after surface mining they had to restore the land to a useful state, and there was a revegetation attempt here, and in order to facilitate that they applied fertilizer and all kinds of soil amendments to enhance plant establishment and growth. So that was a big factorial experiment, but when the students submitted the draft project, the stated hypothesis was there's a difference among fertilizer and soil amendment treatments, and that's in fact exactly what the student tested with an analysis of variance, right? So we're looking for a p-value, that there's a significant difference. Now, does this pass my acid tests, number 1 and number 2? So first of all, deep in your heart, do you already know the answer? Is there a difference or is there none? Sure I do, If I throw on biosolids and straw and all kinds of stuff and evaluate plant growth, there's got to be a difference, right? This is not the same thing. They will surely differ. So there's basically no chance that there's no difference. So what's the point of testing it if I already know the answer? So in statistical terminology, we already know a priori that the null hypothesis is false. And in those cases, there's actually no point to testing this. And if the student is wrong about this, is it still interesting? Well, it seems there's a lot of variability here, and it's quite imaginable that the p-value, although we know there is a difference, is actually larger than 0.05, maybe considerably larger than 0.05. So non-significant. So what does this mean? Is this interesting? No significant result? What a disappointment. So that's very possible, and neither of my acid tests can be passed. If you are analyzing your experiment like this, you're setting yourself up for failure. So what can you do? First of all, if you look at data like this, you may actually have an interesting idea why you see certain patterns. And this could very well be a good scientific hypothesis. So this kind of thought process is how most scientific hypotheses are developed. You see something in your data, you have an idea of why that is, right? Your previous experiment actually becomes the phenomenon, right? You see something here that makes you scratch your head and wonder, why is that? And you come up with an explanation. And so that explanation actually becomes your scientific hypothesis. So the important thing to realize is that the phenomenon itself, so what you see in your experiment, does not normally tell you whether you're right or wrong about your idea, why that is and how that works. So you have to shift gears, and you have to actually come up with a new experiment that allows you to validate or reject your explanation. And that is actually an additional criteria, so an additional acid test that you have now. If you have an idea of how this works, but there's no feasible experiment that you can carry out, that's also a criteria for a good hypothesis. So a good hypothesis needs to be testable. And I should warn you that, if you see something in your data and you come up with an explanation, it may or may not be a good scientific hypothesis. So it should pass all 3 acid tests. You may want to run it by your supervisor before you shift gears. You certainly want to test explanations that have broader implications that are interesting, like the example that we've seen before. So shift gears if you have an idea. That's my first recommendation. Second, thoroughly research the context. Why was the study done the way it was done? What were the objectives? So you have to talk to the stakeholders, companies that had input into this, maybe your supervisor who helped set this up. What was this all about? And even though my p-values may be non-significant, this could be a really exciting result if you understand the context and if you carry out the right tests. So the context here is the standard procedure for the mining company was to use clean fill, so that's clay and soil and gravel, to prepare the site for revegetation. But that's a really expensive proposition, and so the objective was to find other soil amendments that are cheaper. And so biosolids and all the other ones here are really cheap alternatives, and biosolids is actually doing here quite well. So biosolids are the byproduct from wastewater treatments, and they actually pay you to take it off their hands. So you can kind of see that there are no big differences here between the gray and the green bar. So if you actually test different and meaningful alternative hypotheses, you can make powerful statements. So in this particular case, you could make a promise that with 90% certainty, you could replace clean fill with biosolids and not suffer more than 20% reduction in revegetation success. And that is extremely valuable to that company, right? They save a pile of money, they even get paid to take it off their hands, and they still get 80% of the benefits. So by providing the proper research context and testing a meaningful alternative hypothesis, you could provide powerful decision support that was worth hundreds of thousands of dollars. And so if you just do your standard null hypothesis testing that automatically is carried out by ANOVA, you're leaving all that money on the table. So even if you can't come up with a true scientific hypothesis, like in the previous example, you can still make very useful scientific contributions. So not all science is driven by true hypothesis testing. So with that, I welcome you to the course, and I hope you'll have fun in learning all these methods, how to do these things, and then also give it a go and try to apply those to real-world questions or real scientific problems.